This is lesson 2 of the quantum mechanics mini lecture series, historical context part 2. So in the previous video, I talked about what scientists were studying in the 1860s onwards, what was puzzling them, what they couldn't explain using their present knowledge of physics at the time. So let's suppose you have light from the sun coming into your room, hitting, let's say, a glass prism on your table. You would see a rainbow, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Okay, you would see what's called a continuous spectrum. Continuous means there's no gaps in the spectrum. Spectrum means the range of colors that you see. Okay, so you'd see just a rainbow, continuous rainbow. Let's say sodium, as I mentioned before, you would see very specific colors. You wouldn't see this continuous spectrum. Okay, I should also mention more accurately that sodium also has other lines, but the two yellow ones are the most distinctive, the most obvious ones that you can see in an experiment. So two yellow lines on a black background. Okay, this is called an emission spectrum. Emission because the sodium is emitting lines of light of very specific colors. Okay, at around 588 and 589 nanometers. Okay, a nanometer is a billionth of a meter. It's a very small number because the wavelengths are very short, like this, I suppose. Okay. So this is what physicists at the time were expecting from sodium, to see a continuous rainbow spectrum. So different elements were actually found to give different colors and different spectra. So let's say here's a photographic plate. Lithium would give something like this, lines at particular wavelengths. Sodium would give lines at particular helium would give lines at particular wavelengths too. Okay, and the more complex the element, the more the number of lines visible in the spectrum. Okay, so the larger the atomic number of an element, so on the periodic table of the elements, the larger the number of protons or electrons in an atom, the more spectral lines were observed. Okay, this puzzled physicists at the time. And physics at the time was called classical physics. Okay, classical physics is physics which describes everyday macroscopic. Macroscopic means large, everyday large objects like the motion of a soccer ball being kicked into the air, a stone being thrown into a pond. These can all be described these phenomena can be described in very accurate ways, okay, very predictable ways. So classical physics is also known as pre-20th century physics, okay? Physicists like Sir Isaac Newton and James Clerk Maxwell. So Newton was known for his laws of motion. Okay, 3 laws of motion. Maxwell was known for his work on light. And there were also disciplines like thermodynamics, the study of heat and energy in action, thermodynamics, acoustics, optics. These are all branches of classical physics. They all deal with everyday phenomena that we're familiar with. But classical physics couldn't account for spectra of elements. It couldn't explain what was happening, what was the mystery causing elements to give very specific colors of light. That's where quantum mechanics comes in, a relatively new branch of physics. By new, I mean just over 100 years old. Also known as, quantum physics is sort of the application version of quantum mechanics. Quantum mechanics is the actual theory. Quantum physics is the application, so let's say in phones, I believe. People like Max Planck, I'm going to talk about, Einstein, Bohr, probably heard some of these in junior school science, De Broglie, Schrödinger, Born, Heisenberg. So these guys are the main key players in quantum mechanics. Okay, very important work was done in such a short amount of time, actually, in the 20th century. So it's a magnificent theory, very elegant, and we shall see what these guys and how they contributed to quantum mechanics.